So welcome to video demonstration video 3 in ST4 on linear modeling. Here we're going to look at linear regression. So we're going to look at an example where we have a bunch of 5 heights and weights that we know are correlated together. When you plot them like that, we can see that they're correlated with each other, and we can add maybe a color just to see the points more clearly. And then we can add an outline as well through that. And what we can do then is maybe space out the plot just to get a sense of where the intercept is on the plot. So we're going to change the x limits there, and we're going to do the same for the y limits just to space it out a bit more. So you can see that we're spaced out a bit more. We can draw an outline on it there. So I need to adjust it to include the intercept, which is small. There we go. So the intercept is maybe around 14. We can see that on the bottom left of that plot there. When we look at the correlation there, we get a correlation about 0.7. And if we do car.test, we can see we get our corresponding t-value about 1.71. And you see the 95% confidence interval is very, very wide here. So this distribution, although they're correlated with each other, it isn't, if we continue sampling the data, the shape of the distribution could be much more wide, have a wider spread of values here. When you think about the underlying model, we're looking at at the linkage of height and weight together. So if we look at that model, we're looking at a model of weight to be equal to 11.2 times, the height and weight are linked up. That's weight, that should be height here. Weight is equal to 11.2 times my height plus 15.2. So you can see there on the plot, the slope is, the intercept is 15.2 and slope is at 11.2 on this plot. If we take simulated data, so in this case, we're taking runif, that generates 100 numbers between 15 and 19. So if we do this every time, we'll see that the numbers differ every single time and therefore have a slightly different mean, even though they're the same from the same code. It's never the exact same. So we're creating a bunch of heights using this code, and then we're sampling from these heights. We're taking 0.2 by 0.5 by height 2, and we're adding OR norm on from that. We're sampling 100 numbers with a small error time of about between around 0 with a standard deviation of 0.5. So if we do that, we'll get a range of weights for weight 2 and a range of heights for height 2 as well that we can see. We can plot them to see if they're associated with each other as well, using a similar approach to what we had before. And we see that they're tightly clustered together. We're going to turn down the text size so we can see them a bit better. And we're just that this might make it easier to see. It's a bit easier. We can add on a outline to see the point at which this line passes 0, and we can assess the model by taking the linear model of these two. And what we see there is that weight 2 is equal to 0.49 by height 2 within this intercept of 1.1645. So if we zoom out in our plot again, with our outline, you can see there that's where the line crosses x equals 0. We get a value of 0.17, roughly speaking. So for your own data sets, you can make your own pair of data sets using runif again, but create weights as a function of height so that they're correlated with each other. You can use runif or OR norm for that. The numbers of entries in the heights and weights must be equal for that to work, and plot them against each other using as above, and use the LM function to create a linear model and use outline to plot that value. Then you can look at the correlation coefficient value and R² value. You can get more information from the summary function on the model, And then finally, you consider what's the intercept for your model, what's the slope. Can you write a simple linear equation for the response variable weight based on the parameters for its linear relationship height?